This is the 3070 series, so it's a 3071, which is mainly covering level 2 work, with just the last two chapters doing level 3, and 3072, those two booklets. And it's the 91393 standard, worth 3 credits. And I will say the task is a lot easier than the booklets, because they were actually written when we weren't sure what the moderators wanted. So I see Esther is typing, but I'll respond when she's ready. Okay, right. So in the task, because we can leave out a fair number of things in the booklets, in the task basically you have to compare an electrochemical cell and an electrolytic cell. And your achieved merit and excellence grade is looking at your depth of understanding. So the first thing I've tried to show in the CH3001 booklet, that's core concepts, this idea of a triangle where you've got your macro observations, you've got your microscopic or submicroscopic explanations, and then your model representation. So always think of this triangle. And to do well in chemistry, you must talk about all three. So you need to do the macro, which is your colors, and link those to species. So don't just say the orange turned green, the orange what, and the green what. Okay? So, and also put in states. At level 3, we expect you to put states in. Is it a solid? Is it a liquid? Is it a gas? So those are your macro observations. Then you also need to explain it, so on the particle level. So in this context, what is being reduced, what is being oxidized, what's gaining electrons, what's losing electrons, why? So try and explain it in detail on a particle level. And then the model or the symbol is your equations, your formulae, and so on. So those are the 3 things we're looking for, and we're just comparing the 2 different cells. So April, electrochemical and electrolytic. I will show you the electrolytic a little bit later. Now, do any of you sort of go onto YouTube and you look at clips online, on YouTube for explanations? Because there's some great ones out there. This conventional cell diagrams, you don't have to know that section, just in case you were wondering on that. So let's look at, in terms of what I said, this triangle, this explanation of the macro, the particle, and the model. So here's an example, and you can get these on YouTube. It's the reactions, and I'll get them going at the same time, of magnesium metal and copper sulfate, and then copper metal and magnesium sulfate, because this is the way we can see what is the stronger reductant and what is the stronger oxidant. Notice there's a reaction happening in the top one. Okay, you can see something happening there, but in the bottom one, nothing is happening. So what can you tell me of those 2? Which is the one that is more likely to grab electrons? Magnesium or copper? So quite a few of you are typing. The copper, yep. The copper is not giving up its electrons in this bottom one. So you're right, Ethel. The magnesium can't take the electrons from the copper. But if I move this one back a bit, you can see that there is a reaction where the copper has grabbed it from the magnesium, and all this sort of sludge coming down is the copper metal that's being deposited, and you get left with a pitted magnesium metal. So you can see there's a reaction where there's no change in the copper. The copper hasn't given up any electrons. So the copper will not give up electrons. It's not a very good reductant with magnesium, but it is a stronger oxidant. So if those are the reactions, the copper ions will grab electrons from magnesium. Magnesium ions can't grab electrons from copper. So this is what I mean with the macro. We explain what is happening. If I move this back a bit, you would say that, and if you let this go long enough, the blue color of the copper ions would fade to form a colorless magnesium sulfate solution. So I'm just trying to get my thing back. I don't know if you can see it there. Well, it's by the magnesium. The magnesium ion is colorless, so you would have to explain that. Let's just go through to this. I'm just trying to show where the equilibrium lies. You don't have to go into this in much depth at all. We're just trying to show that for copper, it's more likely the copper ions are going to grab electrons to form copper, because copper holds onto its electrons more strongly than the magnesium metal. So that's how we're trying to explain it on the particle level. Okay, and we measure this by using volts. Okay, so we're not looking at the solubility, and we can't measure it directly. So the way we measure it is we compare how strongly it holds onto its electrons compared to hydrogen. So we just make hydrogen 0. We just give it an arbitrary value. We can't measure an exact value, so we give hydrogen a value of 0, and that's this one here in the middle. And magnesium, you can see, is less likely to hold onto its electrons than hydrogen, which means that hydrogen ions will grab electrons from magnesium, but copper will more likely hold onto its electrons than hydrogen. So what's going to happen is copper ions are going to grab electrons. They'll react. So let me get this right. Is copper ions will grab electrons from the hydrogen gas. Okay, so there will be a reaction there. So that's just where, in case you're wondering where those measurements come from, and you will be given those measurements in the task. So you don't have to worry about that you've got to learn it off by heart. Now, quite a few of you are saying, typing, so I'll keep an eye on what you're saying. If your cursor is in that typing chat box, then it sometimes comes up as though you're typing, whereas you may not be. Okay, so the higher values take electrons from the lower value. Yeah, so I don't quite like the word higher and lower, and I know I sometimes do it myself, because when we look at the table, which we'll see just now, the ones at the top of the table are the more negative values. So it might be better, April, to say the more positive. The more positive the electrode potential, the more likely it's going to grab electrons from other ones. Okay. Right. Now, a lot of students get confused between reductant and oxidant, reduction and oxidation. Okay, oxidation and reduction are half reactions. So it's a reactant going to a product. A reductant is a species. So I put this in the book because it's a visual. I'm a visual learner, and this is the way I see it. So you can think it's a species. It's not a thing happening. It's a single thing. So you've got this end called the reductant, and you've got that end called the oxidant. Okay, so they're species. They're not elements. They're species. So like permanganate or copper ions or something like that. Now this reductant is, I put lots of R's in it, and I hope you can see it sort of looks sad. A reductant gives away its electrons. So a reductant is always what? Oxidized or reduced. It's oxidized. Okay, so he's sad because he has to give away, so a reductant is oxidized. And on this side, I've tried to put some O's over there. I couldn't make an O out of his mouth because he just looked too surprised. But an oxidant, he takes electrons. Okay, so he is reduced. So in that example we had with the magnesium and the copper ions is the oxidant because it's grabbed electrons from the magnesium metal, which is a reductant. So there you've got it there, oxidant, reductant, whereas it doesn't work the other way around. You'll get no reaction. And this is when you want to have like an electrolytic cell. It's because the reaction can't work. So if you wanted it to work, you actually have to supply the energy. Okay, whereas this one will work because energy is being given off. And so I was trying to swap it around and it won't work. And that's because, as I say, you've got to have the oxidant comes from the more positive reduction potential, and the reductant comes from the less positive or more negative oxidation potential. So you can have two positive values or two negative values, but the more positive value will be the oxidant, and the less positive value or more negative value will be the reductant. Okay. Because as it's the bigger the value isn't positive, the more likely this reaction will work as a reduction. And remember, the oxidant is always in the reduction. And the less positive or the more negative, the more likely it's actually going to do the reverse reaction. So it's going to go the other way. Right, there are quite a few people typing, so if you want to ask questions, just go for it. And so I was just highlighting there. You always have to have species from the opposite sides. Because these are both written as reductions, you can't have the magnesium ions reacting with copper ions, because unless the copper ions can grab even more electrons from magnesium ions, which actually won't happen because magnesium can't form Mg3+. And you'll learn that in the 3.4 standard, and you must probably know it from the level 2. Okay, so this is a table. Now you would either be given the table or you would be given the potentials just for the species you're working with, and that's the way we've done it in the task at the moment. We just give you a small number of them. We don't give you this great big table, but basically the more negative the value, the weaker the oxidant and the stronger the reductant. Remember, the reductants are always on the right hand side because we're going that away, and the oxidants are always on the left hand side. Can you all see why you'd have the reductant on the right hand side? Not altogether. Okay. Remember, April, a reductant has to give away electrons, because that's what a reductant does. Think of that ant that's sad, it's got to hand something over. So if I try and have a reductant on this side, the way these potential tables are written, they're always written as reductions. So can you see it's gaining electrons to form that? So when you look at a reduction potential table, it's always written as reduction. So if I want to find the reductant, I've got to go the reverse reaction. So can you see lithium loses electrons to form the lithium ion? So that is the oxidation when I go backwards. And so your reductant, because reductants lose electrons, they're handing them over. So the reductant is on this side because we're going backwards from right to left for my oxidation half reaction. So does that make sense? Okay, right. And if you get given a couple, a redox couple, so if I said Li plus Li, and remember you always have the oxidant first and then the line and then the reductant. Okay, so if you have that, just always remember it's always written in that way, the couple, the oxidant first, then the reductant, because that's the way a reduction reaction would occur. So it's always Li plus Li, and you'll never get given it as Li stroke Li plus if you get given the minus 304 volts together with it. It's just the convention, the way things are done. That's the way they decided on presenting the information. Okay, and as we go down, you get the stronger and stronger oxidants because it's the most positive down here, and as you go up, it's the most negative, and so you'll have the strongest reductant. And that's why you'll find lithium used in so many batteries, like your cell phone and so on. So if it's an electrolytic cell, true, Johnny, it's just by convention, if we were giving you the information, we would never write it as Li plus. We would always write it as Li plus Li is equal to minus 3.04 volts. So we'd always give it as a negative value, and we'd always give it as a reduction potential. It's just the way we present the information. And then you may have to do the reverse. Okay. Right. Yeah, so you always get given things as reduction potentials, either in the couple or in the equation. Okay, and then if you wanted to write the oxidation, you would just simply reverse it. Okay, so if we had this, actually I'm going to skip this. I had another example, but I wanted to, so sorry, I'm going to get to this. Okay, so now we want to look at the two cells, the electrochemical and the galvanic. And sorry, I was a bit, when we got kicked out a lot, I want to say if you go to, for instance, the Bozeman, I've forgotten, Bozeman, yes, the Bozeman videos. The Americans, in fact New Zealand's about the only country that I've come across that makes the galvanic cell the electrochemical and the opposite being the electrolytic. If you go and look at other countries like from Britain or from United States and pretty much anywhere else, they refer to electrochemical as being the overall type. In other words, a cell of chemicals that either require electricity or give out electricity. And then under electrochemical cells, they have the electrolytic and the galvanic. In New Zealand, we make the electrochemical the galvanic cell, and the electrolytic as being something different. Just in case you were confused, you were listening to, say, Bozeman Science or those sort of things, and you're going, well, why are we different? I don't know why we're different. NCEA did it like that. So electrochemical in New Zealand is the galvanic cell. Any questions on that? Okay, so D, good to know, yes. Because there are some great ones there from Britain and from the States, and I know it can be confusing. Okay, so you would be, say, given in the task either description or photos or something like that, where we would show you or tell you what happens. Okay, so in an electrochemical cell, you've got two solutions and an electrode in each solution. So I'm just going to stop it there. Oops, sorry, stop it there. And can you see, we try to keep the same electrode in the solution as the type of solution. It just stops the stuff from getting stuffed up with other elements. So we've got zinc in a zinc solution and copper metal. You can't see the brown very easily because it's sort of head-on in the blue copper ion solution. So copper sulfate or copper nitrate, something like that. We can, if we can't have a metal that conducts, that matches, we can use inert electrodes. We can use platinum that won't react, or carbon rods. We can use those as well. Carbon tends to be more reactive, but I don't know if you've ever opened one of those dry cells in an old heavy-duty battery. I find it great fun opening them up, and you can get the zinc metal and you can get the copper electrode that's inside it. So if you ever want to play around with your own chemistry and you're looking for zinc or for carbon rods, look for a used up heavy-duty battery. Not an alkaline battery, just use the other ones. Okay, so you've got an electrode in an electrolyte with the same matching cation and the same thing over here, or you have an inert electrode in your solution. So the voltmeter shows that electricity will be given off. In other words, the reaction is going to work where you've got the stronger oxidant reacting with the stronger reductant. We're not forcing it the other way around. Okay, so it's spontaneous energy is given off, and at the moment what they're saying here, the circuit is incomplete. What do you think is missing? So the electrons can move, they actually move from the zinc, because the zinc is the stronger reductant or weaker oxidant, whatever you want to say it. So zinc metal is a stronger reductant, so the electrons will move there, goes through the voltmeter, and then it'll go through to the copper metal, or actually it sort of goes there to the copper metal. So that's the pathway of the electrons. When the electrons move up there, zinc ions go into solution, and what happens when the electrons come here, the copper ions grab the electrons and plate onto the copper electrode. And Johnny, yes, what is missing here is the salt bridge, because can you see, if I keep on having zinc ions moving into solution, I don't have any counteracting things, so I'm going to get a charged positive solution. Will my electrons leave this area if there's positive cations hanging around? No. Okay. So it's in a way but a redundant question. But you won't have negative electrons leaving if there's a positive source around. They'd rather go here. So you're not going to have a reaction if I don't somehow link this together to equalize this positive so it stays neutral, and to equalize this negative. Because as the copper ions deposit on the plate, I'm going to have, say if it was like copper sulfate, if I had 200 copper sulfate ions, copper ions and therefore 200 sulfate ions, as the copper deposits on the plate, I'm left over with these 200 sulfate anions that are going to be negative. So I need a salt bridge, and let's move to the salt bridge quickly. There's one. Okay, the salt bridge can be anything that will allow a movement of a solution of ions. So it's normally either a glass tube containing a solution, or it could be damp tissue paper, as long as it can allow a transport of, a movement of fluid across. So what happens here, as the copper ions plate onto the copper, the sulfate can start moving up over here, and as the zinc comes off over here, you can have some of the zinc ions moving over, so it equalizes things out. Normally this is dipped into something that's very soluble, that won't react easily, and that's why potassium nitrate is very useful, because all nitrates, if you know your solubility rules, all nitrates are soluble. You wouldn't want to, say, for instance, have something like potassium sulfate, for instance, if you've got a lead metal in a lead solution, because lead will precipitate out with sulfate and you'll get just no iron solution, because it would have all precipitated out. So that's why it's something like a nitrate. A nitrate doesn't get oxidized very easily, because nitrogen can't lose more than 5 electrons, so it's quite stable that way. And potassium also is fairly stable that way. April, you said, doesn't this take a long time to transport? And yes, so what happens initially is I've got this dipped in potassium nitrate. So what happens as the copper plates on, the potassium ions move into the solution, and as the zinc comes out over here, the nitrate moves into the solution. So initially it's all the stuff that's on the salt bridge that equalizes things, and eventually if you run it long enough you could get zinc moving across. You don't want, of course, zinc to come all the way across, because you don't want zinc plating onto your copper and messing things up. Because eventually, actually, everything just slows down and stops, and that's why a battery runs flat. Because when it gets just too, the voltage gets just too different, the difference decreases too much, the battery goes flat. So do we need to include the eventual ion transport? Yes, you do have to explain the movement of the ions and the movement of the electrons. So this is, remember, that triangle, so you have to explain what happens to the colors and the electrodes, change in color, change in thickness, and so on. That's the macro, and you have to also explain the particle level, or the micro. You have to explain the movement of the ions and the electrons, and then also the Y. Okay, meaning thinking of the KCl movement, not the other movement of the ions. Yes, it's good to explain the salt bridge as well, to show that you've understood it. Okay, because that's just to keep the charges neutral. And then, as I say, you've got to explain why the copper is plating on. So you have to use the reduction potentials to explain why the copper ions are plating onto the copper and not the zinc ions plating onto the zinc. Okay, so you have to show you've understood that copper is the copper ions are a stronger oxidant and the zinc metal is a stronger reductant, and use the given reduction potential tables. Okay. And as I say, these don't run long enough that you can actually see the fading of the copper. It will eventually fade if you ran it long enough. And so here I was just trying to show it diagrammatically. As I say, you can use potassium chloride or potassium nitrate. Some chlorides are insoluble. Most of them are soluble, so it's usually okay. It just depends what you're using. Again, chlorides won't work with lead. We give you the electrochemical and electrolytic cell, so you won't have to think, oh no, what's the solubility rules, what, you just have to work out what we have given you, and we aren't going to try and trick you, so whatever we've given you would be soluble. Okay, and then, as I say, the symbol method, or the model, is writing the equations. Now notice I have included states. At level 3, we expect you to include states in all your equations. Okay, level 2, we were just wanting you to get reactants on one side and products on the other side and balancing. Level 3, we're expecting you to look at the finer detail of what those cells represent. So we're looking at, do you know that zinc is a solid? Can you represent that? Do you know that the zinc ions are aqueous? Can you represent that? Okay, now I know quite a few of you are asking questions there or something, because I just see multiple attendees typing. And I don't know what happened there. That came from something else. Okay, well, here we're trying to show the particle level, so please ignore this. I don't know how that got on there. Let me actually escape out of there. Remove that. There, that's better. Okay, so here we're trying to show, now notice this is the salt bridge again, and so we don't have to make it draped over. You can get cells that are connected in this way. Notice it's perforated over here to show that fluid can move through. It's not a solid barrier. I've only given the anions, of course, but obviously there must be cations as well. So if this was a potassium sulfate solution, there'd be potassium ions here as well. So the copper ions are moving towards the copper because it's a stronger oxidant. Zinc is the stronger reductant. So the electrons are moving that way. The copper ions are grabbing the electrons to form brown or reddish brown copper. So I'm trying to bring in the colors as well. That's sort of the bluish copper ion. And once it's grabbed the electrons, it becomes solid copper. It's that reddish brown solid, and that sort of plates on. Whereas here, the gray zinc metal it loses the electrons because they're going over there, and that should be like a colorless zinc. They look pretty much the same, but that one should have been bluish and this one should have been colorless. Okay, so I want a good level of detail in the description of what is happening on the particle level. Okay, now there are some terms we use, like cathode. So we've had oxidation, oxidant, reduction, reductant. Now we've got cathode, and oops, let me go back. Okay, the other one was anode. Sorry, that's up there. It doesn't matter which one you have, whether it's the electrochemical or the electrolytic. The cations always go to the cathode. Reduction always happens at the cathode. So if you think of the word reduction, there's a C in reduction. So that C makes you remind you of the cathode. And oxidation, there's an A after the then it's an A, that's the anode. So it doesn't matter which type of cell you've got, oxidation at the anode, reduction at the cathode. Now, April, I don't get why the ions go to the respective solids. Okay, as I say, you will be given the reduction potentials. So we could give you the copper zinc, we could give you copper with lead, we could give you zinc with cobalt, or, you know, we'll give you two metals and the things, or it could even be non-metals. There's a whole range we could give you. But you get given two things. You need to look at the reduction potentials, and then you need to have a look and see which one has got the more positive reduction potential, and that one will be the reduction. So in the case for the zinc and the copper, zinc has got a more negative reduction potential than copper. So in this case, the copper ions, being positive, are attracted to the negative cathode. Okay, now I might be sort of confusing you, so I'll just stop there because I don't want to confuse you. I've said this anode is negative because it's the source of electrons, and the electrons are being pushed and they're being attracted to the positive cathode. So this is actually more positive than that. So the reason why these electrons are moving over is because this is more negative than that. So electrons move they get attracted to a positive. So an anode for the electrochemical cell or the galvanic cell is negative, and the cathode is positive. But because these electrons are moving in here, copper ions get attracted to it. So although we still say this is positive, the copper ions get attracted to it because there's an excess of electrons that they can grab onto. Okay, whereas here, although this is negative, the electrons are moving over there because that's the sort of the connection, and so the zinc ions move into solution. Okay, and the system is driven because as the electrons go here, the copper ions are grabbing the electrons. So more electrons move over and more copper ions grab the electrons. So eventually the battery runs flat when there are no more copper ions, or when this difference is not big enough to push the electrons over. So there's not strong enough attraction to go over, then it'll stop. And that's normally when there's too few ions here to keep on sucking up those electrons and keeping this positive enough to make the electrons move over. Okay, so as I say, cations to cathode, reduction at the cathode, those are ways to remember. It'll work for both cells. What is different, and we'll see it in the next one, the cathode here is positive, as I said, because remember, we're not adding energy. This is happening by itself. These electrons are being pushed over, not because we are adding the energy, but because this is positive with respect to that. So they get attracted to the positive. So where they differ is that the cathode is positive in the galvanic cell, and it's actually negative in the next one. So here's the electrolytic cell. So you can see it's the same sort of thing. Okay, we've got two electrodes, anode and cathode. Okay, in this particular case, I've only got one solution. You don't ever want two solutions together like this, because it'll just get really mucky. Okay, so in this particular case, it's just zinc sulfate or something like that. You could have made it copper sulfate. It doesn't really matter, depending on what you want, of course. So what happens here is we can force a reaction to happen because we are supplying energy. So we're still having reduction happening at the cathode. So the zinc ions, can you see the cations move to the cathode and they move away from the anode? Okay, but we can force the reaction because we're supplying energy. Now, we may either just have a box here and say positive and negative, or we may just have these lines. If you do physics, you'll know that the short line is the positive end of a cell and the long line is the, it's the other way around. The short is the negative end of the cell, and the long one is the positive. I always think of, if you've got a positive and you're adding the two lines together, you get a long line, and the short line is like a minus that's been put from the horizontal position to the vertical position. Okay, so we're supplying the energy. Now you know that you'd want the electrons, if we wanted the zinc to preferentially plate onto the cathode, then we have to drive that reaction. So the electrons go over here, and now the zinc moves over and plates it. So the zinc moves over, and I didn't really show this clearly because we don't have copper ions plating, but they plate onto the copper metal. So we use electrolytic cells in three different ways. Electrochemical, or galvanic, is just used to, it's a battery. Okay? Electrolytic can be used in different ways, and that's why we use them. Okay, Caleb, I'll answer that just now. We use it for purifying metal. So for instance, in the Bluff where they make aluminium metal, there's an enormous electrolytic cell there to make aluminium, and that's why it's got its own power supply there. I know Iceland also makes aluminium because they use thermal fuel. It really sucks up a lot of electrons. It's particularly for aluminium, because aluminium 3 plus to aluminium grabs 3 electrons for every ion. So it's to make metals. Okay. It's also used for plating. So if you've ever had a gold-plated jewelry or rhodium-plated or anything like that, we can use it to plate. So for instance, if I have a zinc solution here, the zinc ions would plate onto my electrode here. And the electrode could be iron, it could be copper, it could be whatever. So if I wanted a zinc-plated something, this is the way you would do it. And then the third way is to purify things. So say I had some copper and it wasn't particularly clean, it had a lot of other gunk in it, and I wanted to purify it, then what would you have? A pure copper electrode and an impure. So the pure one would be here, the impure one would be there, and the impure copper would go over and plate on the pure one. So you get all this dross that's, say the copper metal was mixed up with the whole, it was an alloy and you had zinc in it and you had all sorts of things. They would all sort of drop at the bottom and the copper would move over. So those are sort of reasons why we would have an electrolytic. It's not important really for the task, but it's just so you know why we have it. And of course, every time you charge your cell phone or you charge your laptop or whatever, you're actually using an electrolytic cell. You're taking your battery and you're reversing it. So you're putting in the current, you're reversing all the chemical reaction so that the battery can be used as a chemical reaction again and provide you energy when you want it again. Okay, so that is actually in a way a fourth way, is those reversible batteries. Now, Caleb, you said, why is a cathode and anode change charge? Right, because in the electrochemical, the zinc was negative because it didn't hold on to its electrons as strongly. So the electrons were being pushed from or pulled from the zinc to the copper electrode because of that difference in potential. Here, if we have zinc and copper, that's not necessary. It's perhaps not the best example to use here, but if, say, this reaction doesn't work, say I've got 2 carbon electrodes or something like that, there's nothing pulling it over, then what I need is to supply the energy. Now, the direction of the electrons just simply depends on the electrons, your battery supply. So here they're going to the positive and from the negative to over here. Now, if the electrons are going over here, you're forcing the electrons over here, which makes this negative. So it's not positive to attract electrons, it's you forcing them there, so this cathode becomes negative. I don't know if that explains it clearly enough. Here we making the cathode negative is perhaps the best way of describing it. So by putting in an energy supply, we're making this negative, so that will make the current, or the current flow through the circuit. Okay, so does the positive end of the battery attract the electrons? Well, yeah, because, yeah, with that, I mean, the electrons will move through and then they'll move back up and again. So it's, yeah, it, just thinking of that, it gets too many electrons. I mean, it's just simply the way a power supply works. So here, there's a little chemical reaction. There's your battery, your electrochemical cell is happening and over here. So that is, if you like, pushing out electrons because of that battery. Okay, and we just can, because we're pushing out electrons here and we've closed the circuit, they'll come back up again because we've completed the circuit. And if you like, yes, it's tugging the electrons back onto the positive side because electrons are attracted to positive. So yes, you could view it like that. Okay. Yeah, I'm just thinking, actually, this is perhaps not the best diagram, having chosen zinc and copper. Okay, and again, it doesn't matter which cell you've got, cations to cathode, and reduction happens at the cathode. Okay, so reduction at the cathode. And then I think also I also had in the booklet red cat to help you remember. So red cat and anox for thinking of anode oxidation, reduction cathode. There's all these different ways you can remember. Okay, it is a closed book assessment task, but it's I think quite easy. You've just got to make sure you add sufficient detail to do well. Okay, so if I compare back to where I was, okay, what's the difference? Pretty much everything's the same except this one needs a salt bridge. Okay, you also tend to have 2 different solutions here. So the electrode in its own solution and the electrode in its own solution. And because these have to be different, you cannot have the same thing over here unless you had an electrode, I mean, unless your oxidant was not a conductor, then I suppose so. So it's 2 different solutions, a salt bridge, and of course the fact that the cathode is positive here and the anode is negative. but go into the same detail of what's happening with reduction and what's happening with oxidation. So when we go to the next one, here you can see we don't have a salt bridge. Okay, we've got a power supply, and that's pushing the electrons over, and the cathode is negative and the anode is positive. Okay, so that's sort of in brief the differences, but what we are looking for is that macro observation. So tell me what's happening to the colors and why on the particle level. Tell me what is happening at the cathode, at the anode, why is it that particular ion and not the other one, and so on. So yes, April, there's one solution in the electrolytic. We could separate them out, that's not the issue, but it's sort of one solution, because if you have too many different ions in here, if you had copper ions in here and zinc ions, then what would happen is you'd have copper and zinc plating on. There'll be first a preferential one that'll plate more easily, but it'll get quite mucky, and so you certainly wouldn't do that if you were trying to make a pure, say, changing impure gold to pure gold or impure copper to pure copper. Okay, so you'd only have one solution. Right, and there we go. And that's, of course, you have to have the power supply. Oh, don't worry about that. Hurry up. Okay. Now, with the cell diagram, as I say, this is not important. So conventional cell diagram or cell notation, you can put it in, but it's not actually important. It does sort of support that you've understood things. But the important thing is that you know that you can explain on the model level that the more negative potential is going to make this the reductant, so it'll form the zinc ions, and the more positive electrode potential will make this the oxidant, so it'll gain electrons and form the copper. And remember, it is a redox process. There's a transfer of electrons, and that is what is happening in a electrochemical cell. The electrons are flowing from the zinc through to the copper ions. If we were doing the electrolytic, and say we had this and we wanted to plate copper ions onto the zinc, for instance, what would happen is we pushing the electrons to flow upwards. So we adding in the energy, so we are pushing the electrons to go up to make it deposit up. It looks a bit clunky like that because it depends on what we've got in solution and whether we want the zinc to go. But can you see, if to go the other way, we have to supply the energy, whereas for an electrochemical cell, because this is the stronger reductant, it gives off its electrons, which gets transferred over. Okay, so you can explain that on the model level. As I say, you can use the cell notation. That is, I think, in lesson 4 or something like that. And we're just trying to show what's happening to the electrons. And oxidation is, remember, the A for anode and the C for cathode, or anox, red cat. Okay, now, does anybody have an issue with the standard cell potential for the cell? If you've gone through the booklets, okay. Now, I know, no, okay, right. There's different ways of giving this equation. The way I've done it, and I've just made it E reduction, so wherever the reduction, not reductant, reduction. So wherever the reduction is happening, which is a cathode, okay, subtract the cell potential of the anode. Okay, so in the case of the copper zinc, the copper comes first and then the zinc. And if we get a positive sum, well, sum is the wrong word if we're subtracting, but you know what I mean, then it means energy is being given off. If it was negative, it means the reaction won't work because there's not enough energy. There's no attraction for those electrons to move from one to the other. It means you've using a weaker reductant with a weaker oxidant. Okay. You may see this done in different ways. You may see this as E reduction plus E oxidation, where you change the sign. Because you're reversing the reaction, you change the sign. You know, from thermochemistry, if you reverse the reaction, you change the sign. So that is another way of doing it. Yep, and John Lee, I know we spoke about that. And I may, when I rewrite the booklets, because there's 2 or 3 people that have preferred that method. Okay, so despite order, you use the E value of the redox pair. Yes. April, just show that you understand that those E naught values, that little naught means standard conditions. If you continue on with chemistry next year and so on, you'll do it when it's you do these calculations with non-standard conditions. So when it's not 1 mole per liter and when it's not 25 degrees. Because I think, you know, from Equilibria, Le Chatelier, and what you did last year, the equilibrium position can change according to temperature. So if we change the temperature, you would change the position, and therefore you would change the voltage. That's why if you put a battery in the sun, you often recharge it a bit, okay? Because by raising the temperature, you've allowed the reaction to go backwards, if you like, so you've got more of your reductant and oxidant that you need again. Okay, but it's also one of the reasons why you don't ever throw a battery in the fire or anything like that, because something bad could happen. It depends on the battery, but it's a good thing not to throw in the fire. Okay, and another reason why, of course, is that batteries tend to be sealed, and so you don't want to put a sealed thing and heat it up, because that will explode. So any questions in calculating this? You are given these potential values, so you just have to decide if you have to subtract this value from that value or the other way around. And if it's positive, you've got energy given off. If it's negative, it means the reaction's not spontaneous and you need to supply the energy to make it work. Okay, and okay, I'm going to skip this because this is just practice, and I'm not going to really deal with the cell potentials. So, okay. So here's your summary of the galvanic cell. Okay. Remember, it's used to produce energy because it's spontaneous, and the E cell is positive. So you would be writing all this sort of thing as well. But you'd be adding just all the detail and the explanation as well. Has a positive cathode, negative anode. Again, that's not important in itself. You need to explain why. So it would be a positive cathode because it is the weaker reductant, and a negative anode because the anode is actually the stronger reductant. So it's the source of electrons. It's giving away electrons at the anode. Okay, and so the reduction occurs at the cathode and oxidation at the anode. That is always the same regardless. And as I say, it can be represented by a conventional cell diagram. So I know I gave links to last year's lessons. That gives it in a bit more detail if you wanted to do it sort of like by the book, and I had more videos up there. But are there any questions? Because we're pretty much at 4 o'clock now. Do you think you're more happy in doing the task? Okay, so don't let the teacher marked assignments put you off, because as I say, they were set up to when actually the standards were still in draft, and I haven't had a chance to rewrite them yet. So this is really what the task is going to be like, and as I say, the devil's in the detail. It's how much you describe and explain is whether you're going to achieve merit or excellence. Yep, so Johnny, it is easy to miss stuff out, so think of, we do have bullet points there in the task, so go back and check, have I written as much as I know about each bullet point. So there's no time limit on this. That's a nice plus about learning from home. You don't have your one period of classroom time to do this. So once you've written your thing, go back, check, have I covered each bullet point in as much detail as I can. Okay. Right, next week I have to go for a follow-up appointment at the hospital again. That's happened last week, sorry, and that's why I wasn't around and I didn't send an email out. So there won't be a lesson each next week. I will try and make it each week, but just I only got the email yesterday from the hospital to say I needed to come in next Wednesday. So there won't be next Wednesday, but there will be the following Wednesday. And we can do anything on here, redox, if you need it. Otherwise, we'll go on to the first external, the 3.4, the 3040 series. But you're welcome to come with questions on anything. Quite a few of you are typing, so... Okay, right. Right, and as I say, these will be as much... Oh, the 3.4, it's the first exam standard you do. It's in the 3040 series, so 3041, 3042. It's the thermochemical properties and so on, the 91390 standard. Okay, and as I say, the more questions you ask, you know, the more I can help you. Otherwise, I'll just jabber on. Right.